Now we're going to be starting another chapter, chapter 14, chemical kinetics. Kinetics, the main thing about this is the rate or speed of reaction. How fast do reactions occur? Some reactions occur slowly. Just think of something like an iron nail rusting or radioactive decay. Okay, but some things are really slow, and there are some reactions that are very, very fast. Think of like some explosion, a chemical reaction, something burning. That could happen very fast. So chemical kinetics, that's what this chapter about. How fast does a reaction occur? What are factors that affects the speed of reaction? And we'll be talking about how we actually can calculate the time of a reaction. Chemical kinetics. That's the title of this chapter. Okay, so on here you'll see that uh, uh, this is this is a giant picture of, well, it's blown in, of a enzyme, something that speeds up a reaction. So if this thing is supposed to, is some molecule that's supposed to break apart, there are molecules in your body called enzymes that help speed up a reaction, make it happen, also known as a catalyst that can make a reaction go faster. So some reactions are fast, some reactions are slow, and since some reactions occur at regular rates, we can use that to, in a way, time things. We can use it to determine, say, how old a piece of cloth, if this is a piece of cloth, uh, that we can possibly use it to determine how old is a substance, because we know reactions occur at a certain rate, and if you know the rate of a reaction, you can, in a way, back calculate how long ago this reaction or this thing might have been around for. And that's a general idea of how we can calculate time of old materials. Okay, like how do you know that mummy was from, the pharaoh whatever time period? Well, we actually know some of the material that's in it chemically, and based on how much is left, we can calculate back how long ago this material probably was from. Okay, so thermodynamics, um, previous chapter, tells us, does a reaction take place? This chapter is kinetics. How fast does this reaction take place? So thermodynamics, there's actually more of it in a later chapter, but does a reaction occur? This chapter is not does it occur. We're assuming it occurs. It's just how fast. It's slow reaction, fast reaction. By the way, how can we speed it up or slow it down? And so the rate of reaction is a change in which the concentration of the reactant or product, change of concentration of reactant or product over time. And the rate of reaction will be measured in molars, capital M molars, molars per second. Molarity per second is how we measure reaction rate. So if A turns into B, the rate of reaction is the change in delta A over change in time. The thing in bracket means the molarity. Whenever you see anything in brackets, the change in molarity of A. So the molarity went from 3 molars to 2 molars. The change in molarity would be 1, okay, over change in time. It will be negative for the reactants because A turns into B. A will decrease. A will turn into B, so A will obviously decrease. If it's for B, the rate of B would be change in B over change in time, where change in B, and again, change in molarity of B, change in concentration B over change in time. And since B will always increase, if you're turning A into B, B will increase, delta TB will be a positive number over change in time. Reactants we usually have negative, products we say is positive. Well, that's because reactants will go down, you'll have less and less. It's like your flour in your kitchen. If you're cooking stuff, assuming you don't buy anymore, it's not like you make more flour, assuming you don't buy anymore, it'll only go down. The amount of products you make, let's say you make cookies from flour, of course the number of cookies will go up, okay? If you're turning flour into cookies. The amount of flour you have at home will always go down, assuming you're not buying anymore, and the number of cookies you make, if you're making cookies, will always go up if you're cooking or you're making cookies at home. Which is why delta A over delta T or reactants always negative, products always positive. Okay. Because the oh, that's what I was saying. Because delta A decreases the time, delta A will be negative. Because you're using it up. Okay, hence that negative sign there. Okay, so if A, the black dots, turn to B, the red dots, okay, as time goes on, notice, hey, never mind the time units, whether seconds, minutes, hours, days, okay, but in 2 units of time, some of the A turns into B, 4 units of time, A turns into B, more and more and more as time goes on. Okay, if you were to graph that, this is what kind of graph you would see in a normal reaction. So in, say, 10 seconds, okay, so let's say each one of these is, each line is 5 seconds. In 10 seconds, you, well, initially you had 40 molecules of A. In 10 seconds, you have 30. And in 20 seconds, you have a little more than 20. 30 seconds, you have about 15-ish. 40 seconds, about 10-ish. Notice it's not a straight line. It's not linear, okay? And of course, if 10 of the A's is gone, A turns into B. In 10 seconds, you have 10 B's. And 20 seconds, about, 18 B's. And in 30 seconds, what is that? About like 25 B's, and so forth. So A decreases, B increases. These are not going to be straight lines. These are not linear. You might have learned also in your Algebra 2 classes, or I think, maybe it's math analysis, that the you have a y equals 0 as your asymptotes, if you know what those terms are. If not, don't worry about it. Okay, so the rate of change in delta A over change in time, rate for is delta B over change in time. A starts decreasing, B starts increasing. And again, these are not going to be linear. So as time goes on, this is of bromine, Br2, turning into bromide ions, which is, by the way, Br2 is a reddish, you can see here, a dark reddish color. Br minus bromide ions are clear. So as time goes on, it goes from this dark orange to what looks like clear as time goes on. Now, if you're trying to measure concentration, you can't just take a sample of, say, the second thing and bring it to a lab to try to see how much bromine is there. Because by the time you get it there, it will continue reacting such that it's constantly changing, that there will be practically none left. So how can I measure it at any instant in time? Well, for this, it just turns out this reddish orange color has a wavelength of light about 393 nanometers. So if you shine a 393 nanometer light through this solution, the more bromine, Br2, you have in this stuff, the more would be absorbed, or in other words, less will be detected. The less bromine, Br2, in here, more light would go through, and more of the 393 nanometer light would be detected. So we can actually, in a way, measure the concentration of the Br2 in time based on how much light of specifically that reddish orange color goes through over time. Because if it's absorbed, then there will be less of it detected. And if there's less of it absorbed, then most of it will be detected. So because the bromine concentration is just proportional, that's what that little symbol means, proportional to amount of absorptions. The more you have, the more will be absorbed. The less bromine you have, the less of it will be absorbed. So in a way, we can, calculate in time how much bromine we have as time goes on. And here are the actual numbers as, say, 50 seconds, 100. So these time intervals are 50 seconds each. Here are the bromine concentrations, okay? So if you're to graph them, this is what we'll see. So at 50 seconds, well, I don't need to describe what a graph is. That's x versus y graphed right there. Notice it's not a straight line. Okay. In fact, I want to get to average rate versus the term instantaneous rate. So the average rate is a change in bromine over change in time, which is change in bromine, the final concentration minus initial concentration over change in time. So what's the average bromine concentration rate in, between time equals 0 to 50 seconds, it'd be whatever the final is, 0.101 minus initial 0.0120 divided by the time period of 50 seconds. It's kind of like saying, actually, maybe I'll give a different example. If I'm talking about if I am driving from home to school, and for nice number's sake, let's say it takes me half an hour and I live 10 miles away. I just want to use nice numbers. So, what is my average rate or my average speed? Rate is equal to, distance equals rate times time, or rate is equal to distance divided by time. Okay, so my distance would be 10 miles divided by my divided by my time, which is half an hour or 0.5 hours. So 10 divided by 0.5 is 20 miles an hour. If I drove 10 miles, okay, let's say I live 10 miles away and it takes me half an hour, my average speed or my average rate would be 20 miles an hour. That doesn't mean that I set my car on cruise control at 20 miles an hour and I just let it go the entire way, because part of the reason why that might be the average, there's stop signs, there's traffic, but also on the freeway, you shouldn't drive 20 miles an hour unless there's traffic, because that's very, very slow on a freeway. How fast are you going at any moment? That's the instantaneous rate. And for a car, the instantaneous rate would be what you see in a speedometer, the rate for a specific instant in time. So at a stoplight, my instantaneous rate should be 0 miles an hour. And on the freeway, maybe I'm going 65 miles an hour. Okay, but my average rate would be, the distance divided by time, or I just calculated about 20 miles an hour. So average rate and instantaneous rate are not the same. The average rate would be, final minus initial over change in time. But what's the instantaneous rate? Well, the instantaneous rate is technically the slope of the tangent line. I know you don't know how to calculate the slope of the tangent line yet because you would need something called calculus to determine that. And this is only high school level, so I doubt you're in calculus, but one day you will, after taking calculus, you can determine the slope of the line, okay? So determine the slope at that specific point on the line. So what is the slope of the tangent of that line? Here it is. It's 296 times 10 to the minus 5. Here, 2.09 times 10 to the minus 5. Here, 1.48. Notice the rate decreases. And that kind of makes sense. Why? Because as you turn some of the BR2 into BR, you have less of it. So the rate at which the reaction occurs will decrease, slowly decrease. So the rate at which these reactions occur will decrease because you have less and less BR2. And so the slope of the tangent line will decrease as time goes on. How fast the reaction occurs actually slows down as time goes on, which is why the slope is not linear, or the overall graph is not linear. Okay, so what if I had determined the slope of the tangent line at every single point? I think that's on the next slide. Here it is. The rate, so the instantaneous rate is right there. Okay, and what we found is the rate is proportional to the bromine concentration. In other words, rate is equal to constant times bromine. The rate depends on what the bromine concentration. The more bromine there is, the higher the rate. The lower concentration bromine, the lower the rate. And in the middle is the middle. So rate is equal to some sort of constant times bromine concentration. What is then K that's constant? Well, K is equal to rate divided by bromine. What if I took the rate divided by bromine? This 4.2 times 10 to the minus 5 divided by 0.012, or any of the numbers, the rate divided by the bromine concentration. That's this column right there. What do you notice about that? Notice those numbers for K, it's about 3.5-ish times 10 to minus 3. These are actual numbers, so that's why it's not, this constant doesn't stay like exactly constant. So, but notice that number, that number doesn't change, about 3.5 times 10 to the minus 3. I know this is 3.48, 3.51, 3.52, but it's at the average 3.50 times 10 to minus 3. The rate pretty much stays, or k, yeah, the rate constant stays, it's pretty constant. So that's what that means. So this K though does depend on temperature, but let's just assuming it actually states here is 25 degrees Celsius. But so this rate at 25 degrees Celsius, the rate of this reaction is equal to that number K, 3.5 times 10 to minus 3, times the bromine concentration. The higher the bromine concentration, the higher the rate. The lower the bromine concentration, the lower the rate. Oh, actually, let's skip that one for now. Okay, actually, in fact, I'm going to just pause for now.